All right, so let's do some examples, or a couple of examples. So first, maybe let's do let's integrate. Let's do x squared plus xy. Okay, where r is going to be given by x, let's say between -1 and 1, and y between 0 and 1. Right? So what is this? Well, let's write it down in one of the forms, one order. It doesn't really matter which one. Maybe let's put the x inside. We can do it the other way around afterwards. So dx, that's where that's the range that x goes over, and y goes over 0 and 1. Right? So it's this guy. Right? So now we keep this and we anti-differentiate over here. So I will have anti-differentiate in x, right? We're doing this integral, right? Where the y is a fixed constant, right? And so as far as the integral inside is concerned, right? So I have x cubed over 3, right? As the integral of the first term. The integral of the second term is x squared y over 2, right? And x is supposed to be between, so let's say x equals -1 to 1 dy, right? So let's write down what that means. So if I plug in 1, I will have 1/3 plus y over 2, right? And if I plug in -1 over here, so I'm subtracting, right? So I have minus, the thing was plugged in -1, and I get minus 1/3, right? Because -1 cubed is -1. Maybe let me write that in here. I'll simplify it next. And then we're still subtracting, so you have -1 squared y over 2, right? This whole thing we're integrating with respect to y. So that equals the integral from 0 to 1 of, I have 1/3, and then I have minus, this is cubed. So this is still minus, right? So it's minus, so plus 1/3. So we have 2/3 over here, right? And then over here, from this, I have y over 2, and then I have minus, and this -1 squared, that's just 1, right? So I have minus y over 2, right? So that's just not there. So it's I'm just integrating 2/3 from 0 to 1, and that's 2/3, right? Now we could do it the other way around. We could have written it as the integral from -1 to 1, and the integral from 0 to 1, x squared plus xy dy dx. So we're doing the y first. So now I integrate with respect to y, so or anti-differentiate with respect to y. So it's x squared y, right? The integral of this with respect to y, the antiderivative, right? Plus xy squared over 2, and y going from 0 to 1 dx. Right, and I can write down exactly what that is. I'm just plugging in. When I plug in 0 for y, both of these disappear. So it's just the guy was the 1, right? So I have -1 to 1, and over here I'm plugging in y equals 0, so I get x squared plus x over 2, right? Dx. Right? Now, well, let's just let's just write it down. You can make it a little easier. Just the integral of this term will just automatically be 0 because it's symmetric. So let's just do it in the in the stupidest way. So we have x cubed over 3 plus here it's x squared over 4, right? X going from -1 to 1, right? So that's because I have the thing evaluated at 1, so it's 1/3 plus 1/4 minus thing evaluated at -1. So it's again -1/3, right? Plus then we have -1 squared, right? So it's just 1 quarter, right? And we have 1/3. This is going to be minus 1/3. So it's again going to be, if I add up these two guys, I get 2/3. And if I add up these two guys, this is 1/4 and then minus 1/4. So it's again 2/3. Yeah, should be 2/3, right? Okay, so you can see that the computation is maybe not too different, but it is a little different, right? Depending on which order I pick, right? And so you can pick whichever one seems easier sometimes. Over here, for example, we could have gone, well, maybe it's better to do the symmetric integral first, because we can sort of use that. I know that the integral of the xy, if I do it with respect, from -1 to 1 with respect to x, the integral is just going to be 0, because that's what it turns out, right? The integral over here, once I plug everything in, right, you can see that those terms actually cancel out, right? So if I notice that, I might say, well, maybe it's this. Maybe I write it as if I know that the integral of this term with respect to x is 0, then I might have simplified my work and just written this x squared dx dy, and then I might have said, well, I mean, now I have a symmetric interval, I have an even function, so I know that's twice the integral of sorry, so I have 2x squared dx dy, and now this is going to be much easier to integrate, right? And actually the y integral, this is going to be some constant, right? And the y integral doesn't even appear here. We're not going to have enough room to write it down, but whatever this is, it does not depend on y, so I know that it's going to be just constant in terms of y. So integral of some constant from 0 to 1 in terms of y is just that, right? So I know it's just 0, 1, 2x squared dx. Ooh, sorry about that. But so I could have made by sort of smartly figuring out what it is, I might have made my work a lot quicker and easier, right? By noticing that. So it's I mean, it's if you don't notice, I mean, there's nothing wrong with doing it like this, right? In this case, both all approaches work, right? There's you could just go through it, sort of turn the crank, and it will work out. But it's sometimes it gets a little crazier in one order than in the other order. Let me just show you quickly one more example. So what if I have what if my r was let's do something simpler. Let's suppose that x is between 0 and 1, y is also between 0 and 1, and let's do the double integral of 2xy e to the x squared y dA over r. Now, if I have this, then you might notice that maybe this is much easier to integrate with respect to x than with respect to y, because it sort of has this thing as the derivative of this with respect to x, right? So this might be good to actually do x first, right? Because over here, so I have 2xy e to the x squared y dx dy, right? And now we do, well, basically we're doing a u substitution. Let's do the u substitution. U is x squared y, so du, sorry, du is, well, here it's the x is the variable, so we're differentiating with respect to x, so it's 2x, and y is just some constant, right? And hey, that's 2xy dx, right? So again, we're doing the integral with respect to x, right? Y is just as if it were a constant, 4, 20, minus 3.1. Actually, it's going to be between 0 and 1, but it's just a constant, right? So let's write this down. So this is still the y still goes from 0 to 1. Let's figure out the limits afterwards. So this times this is the du, right? So I have du and I have e to the u, right? And u goes from, so when x is 0, what is u? Well, when x is 0, u is also 0, right? So it goes from 0, and then it's when let's see, when x is 1, u is y, right? So this goes from 0 to y, right? dy, right? So that's what it is, right? So now I can, that's easy to integrate, right? Easy to anti-differentiate. E to the u, and u is going from 0 to y, right? Right. So I'm just evaluating at y and 0. So that thing is equal to 0 to 1, and I have the e to the y, right? And minus e to the 0, so that's 1, right? So it's this thing, right? And so that's it's really, the integral from 0 to 1 of e to the y dy minus the integral of 1 from 0 to 1 dy is just 1, right? And here the antiderivative of ey is again ey, so this is e to the 1, right? Let me rewrite it, minus e to the 0, right? Minus 1, and then there's another minus 1, right? So it's really e minus 2, right? Okay, and that's not too terrible, but what if I write it as in the opposite order, right? If I, so far, nothing new, but now there's dy dx. So I'm really doing this integral first, and well, let me not do it here because well, maybe I would have enough paper, but basically, now you have to anti-differentiate. I think, well, this is just the 2x and the x squared. This is just some constants, right? But it's basically almost like anti-differentiating y e to the y times e to the y. And it's not too bad. It's integration by parts, right? It's not too terrible, but it's definitely a bit more complicated than this u substitution, right? And you cannot use the u substitution here, because it will still you know, if I let this be u, now I would be differentiating with respect to y, right? So if I'm differentiating with respect to y, then I don't get 2xy dy. I would get, what would I get? I would get 2x dy. So this y would still be there. I wouldn't be able to get rid of it. The u substitution wouldn't really help me all that much. I would still have to do integration by parts. So again, let's not worry about doing that. I mean, hey, we did it over here, right? I mean, there's nothing wrong with you know, you don't have to do it always in you know, in both ways, right? I was just showing so far the previous 2 examples that I did in both orders. Well, just so that you could see that you could do it in both orders. But you just need to do it in one. And so if you're doing some integral like this and it's and it looks complicated, well, try it in the other order. Maybe it's easier, right? And maybe it's just as hard. Yeah, that will happen as well. So, all right. Okay, one more sort of trick for integration, and this is if we have a function that's actually a product of a function of x and a function of y, right? And so if I have an integral over some rectangle of f of x g of y dA, and the rectangle is x is from A to B, and y is from C to D. Well, then let's write it out. We have the integral. Let's do the y on the outside. Doesn't really, it's not really going to matter. So, and the x on the inside. Right, so dx dy. Now, if you notice, when I'm doing the inside integral, the g of y is just a constant, right? So I could pull it out here, right? I could write c d g of y a b f of x dx dy. Well, now this thing over here is just a constant, right? Oh, I mean, as far as as far as y is concerned, right? I mean, it's inside the integral for in terms of y, but there's no y in here, right? So I could pull it out, so let's pull it out front, and so I have a b f of x dx c d g of y dy, right? And it's just the product of these two, right? Now, it's only going to work if f does not depend on y and g does not depend on x. It's not gonna. This is not something that always works for any function, right? I mean, it has to be a product of a function of x and a function of y, and it also you have to be integrating over a rectangle. Now, we haven't so far talked about integrating over something more complicated, but we will. And then if we integrate over something more complicated, well, it's a bit more complicated to do this. So let's do an example of this. Let's maybe suppose that R is going to be where x goes from 0 to 1, and so it's going to be an example. Y goes from let's say 0 to pi, right? And let's integrate sine y, right, times e to the x, right, dA. Well, we have a rectangle. We have a function of y times a function of x, right, you know, in any order, and so we can just write this as the integral from 0 to 1 e to the x dx times the integral from 0 to pi of sine y dy, right? And we can just compute this. This is e minus 1, right? And sine of y, well, the antiderivative is minus minus cosine, right? And cosine is minus 1 at, well, let me just write it, right? I mean, it's minus cosine y y is 0 to pi, right? So I evaluate this at pi. I get cosine of pi would be minus 1 minus 1 1, and then I'm subtracting minus 1, so adding. So this is 2, right? So this is e to the minus 1 times 2, right? Or maybe 2 e minus 2. Okay, that's might be a little easier to compute. Now again, it only works if I have a function of x alone and a function of y alone and a product of them. It wouldn't work if I had, let's say, sine of x times y. It wouldn't work, right? I cannot do this, right? If it would be e to the x times y, I cannot do this, right? Because it would not be a product of a function of x and a function of y. All right?